Welcome to our second training video. So you may have come off your heat pump course, or you may have done the low temperature heating course, and this is just to help you, these two videos to help you understand heat a little bit better. Now in our last video you learned that heat always moves if there's a difference between temperatures. So the temperature difference could be the difference in temperature being what's in our radiator and the room temperature. That's what makes the heat go at different speeds. And then of course our room temperature and what's outside, the temperature outside, is what denotes the speed of heat leaving our home. And we use this seesaw analogy: the greater the difference, the quicker speed moves. Always important to remember that you can't stop heat from moving. If there is a temperature difference, it will move. Doesn't matter how well you insulate a home, you could put a mile thick piece of insulation all the way around it. If there is a difference in temperature between inside and outside, heat will move. It will move extremely slowly now that you've put all that insulation on, but it does move. That's just the laws of the universe. So insulation slows things down, but as we saw in the last video, if we halve the difference in temperature between inside and outside, we halve the speed heat moves, and that always happens whether you've got insulation or not. So let's have a look at our next slide. So in this column, this is our outside temperature, and as it gets warmer outside, the temperature difference between inside, which is usually 21, and outside is dropping. So this means the heat moving out of our house is dropping. And what that also means then is that the heat, or the speed of heat we need to push into the home, can change. If it's 10 degrees outside, it's no good still putting in 10,000 joules per second. Remember, we usually talk about kilowatts, but a kilowatt is 1 kilojoule per second. Remember, heat is moving at speed, and the speed is always changing. So what we've got here, and this, we're using a 1960s home as an example, and 1960s homes got built with single panel radiators. They had no cavity insulation, and yet they might have needed that 10 kilowatts when it was -3, but when it started to get warmer outside, the heat leaving the home slows down. So the speed of heat we need to push into the home, we can slow that down as well. So don't let these numbers confuse you. We'll go through them one by one. Obviously we've got the outside temperature. We've just had a look that the heat needed inside the home is always changing. When I say the heat needed, that's we're supposed to match the heat going into the home with the heat leaving the home. Now, again, this is a 1960s home. Back in the day, 1960s homes were probably having pots and diplomats put in, and they want massive boilers at all. And if you look at the flow temp, we can bring that flow temp down as the outside temperature comes down. Now this isn't exact maths what I've used. Remember, I'm not brilliant at maths, and it will use something called logarithmic maths, but they are very sort of near the mark. What you're seeing there, it does start to change a little bit as radiators start to have lower temps in, because they tend to be more, the heat moves from them more with radiant rather than convection. So your flow temp can go down, and it's always been able to go down whether in an old house or not. So we've always been able to heat houses with low temperatures. Maybe not when it's really, really cold, but as we start to get warmer outside, we can heat all homes with low temperatures. That's just the law of thermodynamics. But look what we were doing. Look over here. And this is actually, funny enough, we're still doing it today. Perhaps not with 80, but we're still pushing 70 degrees to the radiators all the time, whatever the weather temperature, whatever the temperature outside. So we've always got this fixed flow, which means we've got this fixed flow. So we're always pushing heat into the home at maximum speed. Okay, and this this had to happen when we first started putting boilers into homes, when domestic central heating became popular, but it doesn't have to happen now. So why did we always keep flow temperatures high? So obviously, and I think it's fair to point out, there's a lot of talk now around our industry, lots of people looking at our industry, and I think unfortunately people are forgetting the real value of the heating engineers out there that have been keeping people warm and alive. So one of the greatest skills is to be able to go into someone's home and repair their boiler, get it going. And I use my dad as an example. He retired in COVID. He was 74 when he retired. He only ever did oil boilers. He used to work on big industrial stuff and commercial stuff back in the day, but he set up on his own, worked on oil boilers, had 600 customers over 176 villages at one point. And when he retired at 74, he still had customers old enough to be his parents. If they go without heat, it's 9 o'clock at night, they're probably going to die. Now, he can get any oil boiler going in this country. I mean, it helped that he had about 10 grand's worth of kit on his van. Nowadays you can just swap the burner out. But, he could get any boiler going. It helped that his father-in-law helped develop some of that technology. A bit harder with gas, because obviously, as you know, you gas engineers, there's loads and loads of makes and models out there. You can't carry all the spares you need. But being able to get that boiler going for someone that's got their heating on, especially if they've got young killed children or they're elderly, that is an important skill. And I think, unfortunately, there are plenty out there that are forgetting how valuable that is. They're saying things like, heating engineers should know how to do heat loss and rah. Well, I know how to do heat loss, and I'm pretty good with the science of heat. But you don't want someone like me around. You want someone that can get that boiler going. So well done, all of you that do that. I'm just here to help you understand a little bit about the science of heat. Why did we have to have high temperatures? If the radiators didn't always need high temperatures in them, why did we have high temperatures? Well, boilers back in the day used to be expensive, so domestic central heating came from the commercial side of things. There were commercial central heating systems back in the 1800s onwards. After post-war, Second World War, the domestic central heating around Europe started to grow. People had heating in their rooms. We still had things like electric bar fires, gas fires, coal fires. But domestic central heating kind of really started to grow around 55, and then it really started to grow in the sort of 70s and 80s and 90s. But boilers it was the boiler that had to have a high temperature. So as you know, a hydrocarbon flame, whether you're burning coal, wood, gas, oil, hydrocarbon flame has water vapour inside it. Now, if that water vapour hits a metal surface that's around about 54, it's not always 54, it depends on the dew temperature, that depends on the humidity. If that flame hits a surface around about that temperature, the water vapour will condense out, and it used to rot the water jackets on these boilers. Now, boilers were expensive. Back in 1963, you could buy a premium oil boiler for the same price as a brand new mini car. So we didn't want them breaking down. Now, 54 degrees is really hot to our skin, but to a flame that's over 1,000 degrees C, it's piddly. So that water vapour does condense out. It used to rot the boilers. So the R&D engineers around Europe at the time realised, that there was a problem, because we were having to keep these temperatures really high, which isn't energy efficient. And the reason is because the boilers would sort of rot from this condensation forming on the water jacket and spot corroding it. The other big problem that these high temperature systems caused was corrosion. Now, inhibitors came onto the merchant shelves the year I was born, 1971. This year, I think, is when they got invented by Peter at Vernox. Now, they were invented for a good reason, and I think most of the inhibitor companies have forgot why they were invented. It's because we had to have very high temperature systems, and it's physics. If you increase the temperature of the water, you increase the rate of corrosion. So these single panel radiators that were in the 1960s homes, they were getting crudded up very quickly. A lot of people think it was all to do with the fact we had open vented systems. If you got your pump and your vent and your feed and expansion pipe wrong on them, you were pulling in air. And it was all about the neutral point and keeping most of the pipe work under positive pressure. But it's the temperature that was the real big driving force of the rate of corrosion. And unfortunately, the BS 7593, which is the standard that the inhibitor companies wrote, doesn't mention temperature, which is quite strange considering we're all talking about temperature now. You bring your temperature down, you reduce your rate of corrosion. It's simple laws of physics. So we needed hot temperatures going to our radiators, and let's go back to this one. We needed these hot temperatures going to our radiators because it was all about protecting the boiler. So we had a problem with corrosion, but we also had another problem. We're overheating the home. We're pushing heat into the home too quickly. So what can we do about that? Well, this is what they did. They introduced these things. Now, you don't want to be sitting down in your armchair and all of a sudden feeling hot, getting up out of your armchair, turn your boiler off, sitting back down in your armchair. And remember, heat is moving, so you've turned your heating off, but it's 21 inside still cold outside, so heat's still moving outside, and your room temperature is coming down, and you start to feel cold again. So you're out your chair, you go and turn your boiler on. And you're in and out your chair all day long. Now, to save you doing that, something can do it for you. That was what the wall stat was about. These devices were not introduced as energy saving devices. They were introduced to turn the heat off because we were constantly overheating homes. Same with the TRV. TRVs were not introduced as energy saving devices. They were introduced to shut them radiators down. You might have had your children in the bedroom, you're still up watching telly. You didn't want your bedrooms overheating. So this is why these devices were introduced. The control industry is very, very big around Europe, and I think they may have forgot why their own technology was actually invented in the first place. Let's look at radiators. So the radiators are a very important part of the system. They kind of have been sort of forgotten about a little bit. So again, don't worry about these numbers. Let's go through it separately. So when you buy a radiator, radiators get tested, and that's another big problem. A lot of radiators haven't been tested now. But when you buy a radiator, here's a 600 by 600, type 21, so it's got two panels, and it's just got one convector in between it. When you buy a radiator at catalogue or online, it'll give you its power rating. This one's 807 watts. And that power rating comes from having a certain flow temperature going to the rad, a certain return temperature, and a certain room temperature, and they call it a DT50. The DT50 stands for the difference between the mean water temperature in the radiator and the room temperature. Now, if you change the room temperature, you change the power of their output. If you change the flow and returns, you're going to change the power of the output power of the radiator. Let's have a little look. Remember, it's all to do about this speed. So watts has these seconds built in, all to do about speed. So if we look at this radiator, we've got a flow of 60 degrees, we've got a return of 50 degrees. In between 50 and 60 is 55. So that's kind of going to be the average water temperature inside that radiator. Kind of, remember, sometimes it uses this logarithmic mathematics. But 55 is going to be sort of the average temperature inside that radiator. We call that the mean water temperature. That's all to do with the average water temperature in there. So if it's 55 inside that radiator, the difference between 55 and a room temperature 21 is 34. So we've got a difference in temperature between the room temperature and the water temperature inside the radiator of 34, sorry. That's what's driving the speed. Remember, it's this difference. Remember the seesaw. It's this difference in two temperatures that drives the speed of heat. So that speed is now 482 watts. Okay, a bit different to that. If we had it at a flow temp of 60 and we got a return temp of 40, so there's 20 degrees difference between these two. The difference between these two is 50, so the difference between 60 and 40 is 50, so the average temperature is going to be around 50 degrees in that radiator. And the difference between 50 degrees inside your radiator and 21 room is 29. So we haven't got a greater distance here than we had here. So the speed of heat moving into your room is now slower. Now, interestingly, look, if we look here, we've got a flow of 55. Now, that's 5 degrees cooler than the flow here of 60. But our return is a bit higher. We've only got 5 degree difference between the flow and return. So in between these two is 52.5, which means 52.5, the difference between 52.5 and 21 is 31. So the difference here is higher than here. So now the radiator is actually pushing heat into the home quicker. Even though the flow temperature here is 60 and the flow is only 55 here, if you work out the difference between the mean water temperature, the average temperature in the radiator, and your room temperature, the difference here is greater than what's here. Remember that seesaw. The greater the difference, the quicker things will move. And obviously, as we get lower flow temperatures, the radiator becomes less powerful. So this is why radiators are very important. Lots of people talk about oversizing and undersizing, but radiators are doing different things at different times. And if we go here, look what happens if we change the room temperature. Remember, it's the room temperature and the average temperature in your, it's the difference between the room temperature and the average temperature in the radiator that's driving that speed. So if you drop the room temperature, you're getting a bigger difference between the mean water temperature and the room temperature. So the speed is increased. So that radiator we saw a little while ago, this is what it was doing when it was 21 with different flow and return temps. This is what it would do with them same flow and return temps if the room temperature was 18. And as you can see, the radiator becomes a little bit more powerful. So when people say, you know, turn your thermostat down, most people kind of in their minds know that that's a good thing, it's going to save energy. They probably didn't realise it's also making your radiators a little bit more powerful. My business partner and I have created an app. You can scan your radiator with the app, and then you produce a report. You have to pay for the report, and the report tells you what all your radiators can do in your home at different flow and return temperatures and at different room temperatures. So if you want to design a heating system with room temperatures at 18, it'll tell you what all your radiators are, what their total power output is, as well as individually. I'm not a techie person at all, but the app uses things like LiDAR and augmented reality to measure your radiators. If I'm honest, I don't kind of trust that. We've got a feature on it where you can actually just, you know, sometimes you know how high the radiator is without measuring it, and you just put in 600, get your tape measure out, measure along, find out what that is, and you can actually put that into the app, and then you're going to get a more accurate representation. Again, it's not going to be mega accurate with these things. Like, it all does depend on how you've piped the radiator up as well, but you're going to get a really good idea for what the radiators can do in a home. Actually, it's a bit easier to work out what your radiators can do in a home than actually working heat loss. Heat loss actually is quite a hard thing to really measure properly. But we're getting there. So I hope that was really helpful. And thank you very much for watching. Watch it again if you think you need to sort of understand the maths a bit more. But thank you very much for watching.